So in our next section, we're going to look at our first point-to-point layer 2 VPN variation, which is going to be L2TPv3. We'll see that the configuration of this is very, very straightforward. There's only a couple commands that we need. And then the requirement for this, again, in terms of transport, is going to be basic IP connectivity between the endpoints. Now, there was a question here, can L2TPv3 be used to transport IPv6 over IPv4 and vice versa? Yes, it can. Well, not vice versa, because it's tunneling over IPv4. I'm not 100% sure if there's a v6 native encapsulation format of it, but it's essentially an overlay tunnel, so you can put whatever you want inside of it. It's going like Ethernet to Ethernet, so whatever is encapsulated inside of Ethernet is independent of what the overlay transport, which would be basically your IP routing network in the middle. Okay, so let's take a look at the L2 VPN topology. And this is going to be a little bit different variation of what we had seen from the previous examples. And the reason why I want to talk about the changes here in the virtual topology first, as they relate to what you would need to do in order to allow for L2 connectivity to work in the virtualization. So in most of our previous examples, we basically have the logical CSR 1000Vs and the logical XRVs that are all plugged into one giant virtual switch. And then they're separating the traffic based on the .1q VLAN tags, basically the sub-interfaces that the routers are configuring. Now, the problem with that, though, is that if we're doing layer 2 bridging over that same segment, you effectively create a bridging loop inside of the virtual switch. So when you go to actually try these exercises out later, whether it's like in Viral or directly on CSR, like on ESXi, what you'll need to do is basically create additional virtual switches that are separating the layer 2 traffic. Okay, so this is the effective logical result of what the diagram is going to look like. But when we think about this from a physical point of view, basically what happens is that all of the routers, like routers 1, 2, 3, 4, etc., these are all plugged in on their gig 1 interface that is going to vSwitch number 1. Okay, additionally, some of the routers have additional vSwitches, like router 1 and 2 are plugged in together to vSwitch 2. Okay, that is their gig 2 interface. Router 2 also has a third vSwitch on its gig 3 interface that is going over to, I believe, router 9. Okay, from router 9, that is gig 2. Okay, these interfaces facing in here are gig 1, and so on and so forth. So there's a unique virtual switch that's going between these two, between these two, between these two, and then between the XRs. Now, the problem with the XRs, unfortunately, though, is that layer 2 VPN is not supported in the data plane. You can configure it. It'll take the syntax, and it will establish the control plane both for creating the pseudo wires with either LDP signaling or with BGP signaling, but there's no way to test that it's actually functional because the bridging happens at the encapsulation happens at the line card level, so it's not supported in the virtualization. Luckily, with CSR 1000V, since everything runs in software, it is actually supported to do the bridging, and we'll take a look at those variations. So you can basically follow this along with XRV, but within the scope of the exam, I would assume that they're really not going to test on that a lot because there's no way to really tell 100% for sure if it is actually functional or not. Okay, so next let's take a look at where this is located in the documentation. Okay, there's going to be a couple different syntax formats that we're going to look at. The legacy versions first because there are only a couple commands to use, and then the newer syntax format, which is going to be the unified L2 VPN protocol CLI. So first we're going to start at regular iOS from the iOS XE config guides. And under configuration guides, we're going to go all the way down to the bottom, and this is under wide area networking. Okay, it's the last configuration guide. So under WAN configuration, we have layer 2 services. And then we have L2TPv3, and then also layer 2 local switching. Okay, layer 2 local switching is basically like being an Ethernet bridge, that you're taking a packet in one link and then you're connecting it back out to the other link. From a configuration point of view, it's basically only one command in order to do this. Like if you do Ethernet to Ethernet, you're saying I want to do a connection. I give it a name. I'm connecting traffic that comes in this interface to that interface. Okay, in this case, it's basically bridging two separate VLANs together. Now, the provider edge device in this case doesn't run spanning tree or any other type of layer 2 control plane, so you do have to be careful with L2TPv3 and with any of these other variations like AToM, for example. You can cause a layer 2 bridging loop that could negatively affect the data plane. We'll see in the case of VPLS, there is a basic split horizon logic that's built in to try to fix that problem, but there are ways to break it if you configure it wrong. So don't be surprised if you're playing around with this for the first time on your virtualization, you misconfigure it, and then the CSRs crash, or you lock yourself out of the CLI if the CPU goes to 100%. Yeah, so this first variation where you're basically connecting locally, pretty straightforward. I would assume that they probably wouldn't even test on this in the exam, because it's just one command in order to do this. So for example, here between router 1 and router 9, we have all of these devices here are on the same layer 3 network. And then the provider edge routers are going to be the ones that are taking the layer 2 traffic in and then bridging it across. Okay, bridging it across like over an AToM tunnel, an L2TPv3 tunnel, or over a VPLS multipoint tunnel. Now for local switching, this would be like between router 1 and router 9, where on router 1, if we look at the show run pipe section OSPF, we're running OSPF on every interface. Okay, the same is true for router 9, router 7, and router 8. If we look at the show IP interface brief, we have our quote-unquote physical port that's going, again, to that dedicated virtual switch that's going point-to-point between us and router 2. And if we were to look at this from a CDP point of view, so globally, let's say CDP enable, or actually CDP run. On the physical port, we'll say CDP enable. And then the same thing on router 2. So CDP run, on gig 2, CDP enable, and then same on gig 3. Okay, router 9 will do the same thing. So CDP run, gig 2, CDP enable. Okay, from router 2 then, if we look at the show CDP neighbors, we should see here shortly that we're directly connected both to router 1 and to router 9. Okay, so let's make sure those interfaces are actually up. Show IP interface brief. And gig 2 is up. Let's check on router 1. Show IP interface brief. Gig 2 is up, probably because I didn't exit out of the interface. Let's show CDP neighbors. Okay, now we see router 2. Okay, so for the case of local switching, this would basically be saying I'm going to take every layer 2 frame coming in from router 1 and then just send it out the interface going to router 2 or router 9. But notice here we're not making a bridging decision, so router 2 would not be learning MAC addresses for the customer attachments. Okay, these interfaces from this type of configuration point of view, these are considered to be the ACs, or the attachment circuits. Attachment circuit is basically the link from the provider edge to the customer edge. In the case of L3VPN, the attachment circuit is the link you're running your PE to CE routing on, like your OSPF, EIGRP, RIP, whatever, that's going between the CE and the PE. Okay, so again, in the case of local connection, we would just go to global config, say that we want to do a connect, and we'll give it a name. We'll say that this is local switching. And we say that the local interfaces are going to be gig 2 to gig 3. Okay, so there's other options under here. Actually, in this case, there's not really any options under here. We'll say no shut. We'll see for the X connects, there will be other options. But if we now look for between a router 1 and a router 9, and if we were to look at the show CDP neighbors, we can see that from router 1's perspective, it thinks it's now directly connected to router 9. From an IP routing point of view, if we look at the show IP OSPF neighbors, now router 1 and router 9 are directly adjacent because 2 is basically effectively physically connecting them to send any layer 2 frames that are coming in from router 1 over to router 9. So again, point being here is that it doesn't care what the payload is. If it's IPv4, IPv6, etc., it's just taking the Ethernet frame directly between them. And the other way that you could test that this is working is to ping the broadcast address. Okay, if router 1 and router 9 are logically in the same layer 2 segment, then they should be in the same broadcast domain. Okay, likewise, we can tell that based on OSPF. OSPF is using a link local multicast. It's not routed between them, so we can see that that is being flooded, and we're directly able to reach each other. Okay, the other variation, though, is when we want to do this over the IP network. Okay, this is going to be under, again, WAN configuration, under layer 2 services, and then under L2TPv3. Okay, now if we look at just their config examples, there's, from a minimum configuration point of view, really the only thing that we need to do is to configure the L2TPv3 pseudowire. Okay, from here, mainly what this is going to say is two variables that we must define. What's the encapsulation and where is the tunnel being sourced from? We'll see in the case of an AToM tunnel, which is over MPLS, you don't need to specify the source address because LDP is automatically choosing the loopback as the router ID. But in the case of L2TPv3, since we're not running LDP, it's not related to MPLS, we need to specify what is the local interface. This is basically the source of the tunnel. Okay, then we're specifying the encapsulation is L2TPv3. We then take this pseudowire class and we're going to apply it at the link level. So at the link level, we say we want to do a cross connect or an X connect. What's the address that we're trying to reach? What's the virtual circuit ID that we agree on? And then what is the pseudowire class that we're using? The important thing about this output here is that the virtual circuit number needs to match between the endpoints. The same is going to be true for the AToM tunnels. If I use circuit 10, you need to use circuit 10. It's only locally significant between the two of us. So between multiple interfaces, you can reuse the virtual circuit ID, but it does matter between the two that you're actually creating the point-to-point connection between. Okay, so let's say in this case that we're going to do now the tunnel between router 4 and router 5. So let's break the connection directly between them. So we're going to have to route over a couple hops in order to get there. So we'll go like this direction. So on router 4, let's say that this interface here, which is gig 1.45, that's going to be shut down. And we're going to ping to 5555. Source is our own loopback. So once our IGP in the middle converges, which in this case was OSPF, we have reachability between them. If we do a trace route, we should see that we're hopping over router 6 in the middle. Now in this case, the core is already LDP enabled. We have OSPF plus LDP autoconfig, but that's not going to be required for L2TPv3. It's going to be encapsulated in IP, not encapsulated in MPLS. And we'll see that when we look at the data plane difference between the two encapsulations. Okay, so again, the first step for this is to create the pseudowire class. We'll call this L2TPv3. We say the encap, L2TPv3. And the IP local interface, this is our source of the tunnel. So loopback 0 in this case. Now, as opposed to MPLS tunnels, you don't necessarily have to use the loopback because we're not label switching, but in most cases you typically would. If there's only one physical interface and you're not advertising a loopback, then yeah, you can use the physical link as the source. Okay, then at the interface that's going to the customer, which again is our attachment circuit, if we show run interface gig 2, we're basically going to say that any traffic that comes in this interface is going to go in the layer 2 tunnel, and the destination of the layer 2 tunnel is going to be the loopback of the other guy, router 5. So we say on the physical link that we're going to do an X connect. Destination is router 5's loopback. Virtual circuit ID we'll say just is number 1. And the pseudowire class is L2TPv3 is what I called it. Okay, under the X connect, there's other options that you can configure, like you can have a backup tunnel. If the primary one goes down, you could forward to another destination. What this allows you to do is have active standby forwarding, because if you did active forwarding, you would cause a layer 2 bridging loop potentially. So if the customer edge is running spanning tree, then that's fine. You can have multiple tunnels, and then spanning tree would do the root port election and the blocking interfaces. But anytime you have multi-point layer 2 bridging, you have the potential problem for causing a layer 2 loop. Okay, so pretty straightforward. It's basically just like 4 commands here. So let's say show run, pipe section, xconnect, or pseudo wire. And we'll basically do the same thing on router 5. So on router 5, we'll say globally, we have our pseudo wire class. Then at the port level, we have our xconnect going over to router 4. Circuit ID we agree on is number 1. Pseudo wire class is L2TPv3, which I created. Okay, then for verification, if we look at our show L2TP session, okay, we should see that we have a circuit that is established to the other side. If we look at the L2TP tunnel, this will tell us the details. Or actually, maybe it is L2, is it L2 tunnel session? There is a detailed output here, which is what? Show L2. Let's look at the documentation. There's an output that shows you all of the details of the tunnel, how they negotiate. Or actually, it's probably show L2 transport. Show L2. Now, the syntax is different on this guy. Okay, let's look at what is the verification. And we'll see this is the legacy syntax. There's a new unified format that makes a little bit more sense because it's the same between L2TP, AToM, and VPLS. So let's go to verifying an L2TPv3 session. Show L2 tunnel session brief. Show L2 tunnel session all. This is what I'm looking for. Okay, so from in here, the key points would be what is the IP protocol. So this is the transport between them. It has its own number, which is 115. This means that if you needed to permit this through a firewall or through an access list, this is the IP protocol number. It's not a port number. So it's not a TCP tunnel. It's its own separate layer 4 protocol. It says that the tunnel is established, and then you can see the counters for it. Another important point here would be the MTU. So since we're adding additional overhead, this means that the effective MTU of the customer edge is going to be lower unless you enable jumbo MTU in the core. So here, if we were to look at between the customer edge devices, which are router 7 and router 8, if we were to go to router 7, and notice here that we formed an OSPF adjacency if we show IP OSPF neighbors, and if we ping the broadcast address, we should get a response back in from router 8. Now, if we look at this from a packet capture point of view, so I have the Wireshark box in the middle, and what we will see is basically just packets that are tunneled between router 4 and 5. So let me do a couple pings here. Let's ping 8888, source 7777. Let's send like 100 packets. Okay, so these are the actual pings. And in here we see that it's the outer Ethernet header, which in this case is what we're tunneling over. MPLS in this case is there because this is running in the core, but this is not going to be needed. Where the layer 2 tunnel is IP with protocol 115 inside of it. And then we have inside this is the payload, which is the actual Ethernet frame. So it doesn't decode it here. Wireshark can't see what the payload is. But if you were to look at like this here, ABCD, ABCD, this is the default pattern of what the ping is between the two of them. And also if we looked at like the MAC addresses between router 7 and router 8, on router 7, if we show interface gig 2, pipe to include the burned in address, we have 4CA4, which is right here. Okay, 005056AD. So basically that's the source MAC address inside of the Ethernet header. So pretty simple configuration. And again, the only requirement for this is that you have IP transport in the middle. If we were to go to router 7 and do a ping again and then say that we're going to set the don't fragment bit, and if we set the size to 1500 bytes, this is going to get, or let's say 1504, then it's going to get dropped in the middle. So the router can do fragmentation for the layer 2 tunnel itself, but anytime that you're adding additional encapsulation overhead, the MTU could potentially be a problem. Just like in our L3 VPN variations, every time you add an additional MPLS label, you would need to account for that in terms of the MTU. Okay, so to recap real quick, if we look at just the this output here, and let's say show run pipe section, pseudo wire or gig. Let's look at the interface. Okay, so the interface level just has the X connect directly on it, which was similar to what we did on router 2 in global config, which is just a connect. So a connect is for 2 local interfaces. An X connect is for a remote cross connect, so it's either encapsulated over IP or L2TPv3. Okay, so this is basically the legacy syntax. Now the other variation of this is that if we go under, not under WAN configuration, but if we go under MPLS, this is where the rest of the layer 2 tunnels are going to be documented. Okay, so let's look for label switching, MPLS, not command reference, we want the config guide, and then under L2VPN. Okay, first document in the newer versions is the L2VPN protocol-based CLI. This is the new unified format that is the same between all of the different platforms. So it shows you here in what particular release this was available, and then what are some of the examples of them. Okay, so previously we had done globally an X connect that says we had the members that were the different IP addresses. The way that it works now is when traffic is received on an interface, you classify it based on what is called a service instance, and then the service instance is the one that is part of the logical bridging between the 2 circuits, either a local circuit or to a remote circuit. Now, the reason why it's implemented this way is that there's some platform limitations that if we were to do something like this, so let's say that this subinterface is using VLAN 30. If we were to say interface VLAN 30 and then do an X connect on here, this is what the legacy syntax used to be, and you would say X connect 10.0.0.1. Then we would go to this port and basically say this is running VLAN 30, like as an access port, or it could even be a trunk port going down to the customer. The limitation of this was that when you create the layer 3 SVI, it's also reserving an internal VLAN number, which reduces the total number of VLANs that you can use down to the customer segments. So the way that they fix this problem is to say, well, let's use this service instance that's not used for regular layer 2 switching. So it's not part of the regular global MAC address table space or not part of the global internal VLANs, but instead we're going to use this just for these L2VPN cross connects, like in this case, or we'll see in the case of VPLS, we're going to create what's called a virtual forwarding interface, a VFI, where the members are going to be the physical ports and their associated service instances, and then whatever the remote destination would be.